Hello everyone and welcome to my channel Chemistry by Miss Nidhi Banga. Today we will be talking about or we would be reviewing the chapter DNF block elements. The thing is, I feel it's much more effective if you review the chapter through questions. That means while solving the questions from each topic, the whole chapter should get reviewed. It's much more effective and much less boring than reading the NCERT book. So I have broken down the topics and we have chosen some questions which were from previous year board questions or important questions. So let's get started. So the first question is, why zinc, cadmium and mercury are not considered transition elements? This is the first important topic on the first page of the chapter. Now, D block elements are the ones where the last electron enters into the D subshell. Zinc, cadmium, mercury are D subshell electrons, all right, but they are not transition elements. Okay, they are D block elements, but they are not transition elements. Why? Because transition elements have their own definition. Transition elements or metals are the ones which have incomplete D subshell in ground state and their common oxidation state. It's and, that means they have to have incomplete D subshell in ground state and common oxidation states both, not either one of them, both. All right, now let's talk about these three elements. When we talk about zinc, its electronic configuration is argon 3d10 4s2. Cadmium would be krypton 4d10 5s2. Mercury is xenon 5d10 6s2, 4f14 as well. Okay, now the thing about these elements is that you can see that they have completely filled D subshell. If they have completely filled D subshell in the ground state, that is one condition not met. The other condition is in the common oxidation state. So these elements show only one oxidation state, and that is +2 oxidation state. Now in +2 oxidation state, the electronic configuration would become the same minus the electron in the S subshell. So zinc would be argon 3d10, cadmium would be krypton 4d10, mercury would be xenon 4f14 and 5d10. The D orbital would still be filled, right? So these three elements do not meet the condition which we have for transition metals. That is why these three are not considered transition elements. This is one of the most commonly asked questions in boards. Next up is copper, silver, gold are considered transition elements even though they have ND configuration. Explain. Now let's start with writing their configurations. Copper has argon 3d10 4s1. Silver is krypton 4d10 5s1, and gold is xenon 4f14 5d10 and 6s1. Now let's think about the oxidation states. Now here we can see that in ground states they have the D subshell filled, but let's talk about oxidation states. Copper shows +1 and +2. So in +1 it would be 3d10, in +2 it would be 3d9. Silver also shows +1 and +2. So same situation, 4d10 in +1 and 4d9 in +2. Gold shows +3. So it would be 5d8 in +3 oxidation state. So there you have incompletely filled or incomplete D subshell in the oxidation states. Okay, I hope you can write the configurations just like I said. All right, so this is about the definition of transition elements. Now let's talk about how their properties change when we move along the period. The properties of transition elements change. How do they change when we move along the period? Atomic number, as we move along the period, obviously atomic number would increase. Metallic radius. Now metallic radius depends upon, or radius, atomic radius depends upon Z effective. Now what do you think would happen to Z effective or effective nuclear charge? As we move from left to right, protons get added into the nucleus. Electrons also get added, but they get added in the same shell. So distance from the nucleus does not increase. Nuclear charge keeps on increasing, but distance of the electrons, added electrons, does not increase much. Okay, so the electrons, the outermost electrons, feel more pulled towards the nucleus. Okay, that is why Z effective or effective nuclear charge increases as we move left to right along the period. Now, since the effective nuclear charge increases, it's going to pull the electrons towards itself. The nucleus is going to pull the electrons. That would result in shrinking of the atomic radius as we move from left to right. So that is what happens. Metallic radius decreases as we move left to right. Atomic mass, obviously atomic mass is going to increase because as we go left to right, number of protons are increasing, right? So number of protons and neutrons, they're both increasing, so atomic mass keeps on increasing. Density. Density is mass by volume. Now let's see. As we move left to right, atomic mass increases, volume decreases. If numerator keeps on increasing, denominator keeps on decreasing, so density would keep on increasing. So as we move from left to right, density increases. Ionization energy. Ionization energy is the energy required to pull the outermost electron. It's not the proper definition, but loosely, this is what it means. That it's the energy required to pull the outermost electron. Now, obviously, as we move from left to right, we have seen that metallic radius decreases. Metallic radius decreases, that means the outermost electron is getting closer and closer to the nucleus. So it's going to get harder and harder to remove that electron. That means it's going to require more and more energy to lose the electron. So as we move from left to right along the period, ionization energy tends to increase simply because size tends to decrease. Covalent character. Now when we talk about covalent character or ionic character, we look at various things. We look at the charges on the cation. We look at the size of the anion. We look at the charge density of the cation. Now why is that? When we have a compound, polarizing power of metal matters and polarizability of anion matters. Polarizing power of the cation depends upon the charge density. Charge density means how much charge in how much area, in how much volume. So obviously, if you have a smaller cation with a higher charge, that's going to have higher charge density. Polarizability depends upon how diffusible the anion is. Diffusible means how big the anion is. If the anion is very big, it can be easily, its electron cloud can be easily molded. It can be easily manipulated. So that is, these two things of cation and anion matters. Okay, so what actually is covalent character? If your cation is small size and high charge, that means it has high charge density, and if your anion is quite big, the cation would be able to pull the electron cloud from the anion towards the center. When the electron cloud is in the center of metal and the anion, then obviously that is covalent behavior. Covalent character means that the electrons are in the center, being shared between the two. Ionic character, on the other hand, means the electron is mostly towards the anion and cation is quite positive, doesn't have the electron, right? So covalent character means when the cation is able to pull the electron cloud of the anion into the center, in the middle, right? So it depends upon these two things. So whenever we will be talking about covalent character or ionic character, we will focus on this. It's called as Fazan's rule. This you did in grade 11. Now, reactivity. Reactivity is directly related to ionization energy. Lower the ionization energy, more easily the metal would lose electron. That means more easily it would react. Higher the ionization energy, opposite the trend. Higher ionization energy means it's more difficult to lose the electron. It would rather not lose the electron. That means it would rather not react. So high ionization energy means low reactivity. So along the period, since ionization energy increases, the reactivity would decrease. Okay. Basic character of oxides. As we go along the period, the ionization energy increases. That means metallic character decreases, because what is metallic character? Metallic character is how easily a metal atom loses its electron, right? So if ionization energy is increasing, that means metallic character is decreasing. If metallic character decreases, that means the basic character also of oxide also would decrease, because metals have basic oxides and non-metals have acidic oxide. If its metallic character is decreasing, the basic character of its oxide would also decrease. Okay, now we shall see how we can put this knowledge to use. Next question is, these are all both questions, by the way. So next question is, the halides of transition elements become more covalent with increasing oxidation state of metal. If let's say we have MX and then we have MX2. Here the oxidation state of metal is +1. Here the oxidation state of metal is +2. Now we know that the cation, we're talking about the same metal, by the way. So when we are talking about a highly positive cation, so that means it has high charge density. Why high charge density? One, its charge is high. Second, upon losing the second electron, its volume also decreased. So it has high charge, low volume. That means high charge density. High charge density means it has high polarizing power. If it has high polarizing power, it's going to pull the electron cloud of the anion towards the center. That means it's going to have more covalent character. So, as the oxidation state increases, the polarizing power of the metal ion increases. Since polarizing power increases, it's going to pull the electron towards the center. That's what covalent character is, right? Okay. Reactivity of transition element decreases almost regularly from scandium to copper. Explain. Scandium to copper, that means along the period. Reactivity decreases because size decreases. Size decreases, therefore ionization energy increases. That means it's more reluctant to lose the electrons, therefore more reluctant to react. Okay. Next up is basic character of the transition metal monoxides. Follow the order: titanium oxide to vanadium, then chromium oxide, then iron oxide. As you can see, this is along the period situation. If this is along the period, basic character decreases. That is because metallic character decreases. Metallic character decreases along the period. If metallic character decreases along the period, obviously the basic character of oxides would also decrease. Now, why metallic character decreases? Because ionization energy increases. along the period. Now, why does that increase? Size decreases. Size decreases, ionization energy increases. Ionization energy increases, metallic character would decrease. That would mean that the basic character of oxide would decrease. Okay? Moving on. Now we will talk about the general properties of the transition elements. Now, transition elements show a variety of properties. Many questions are asked directly. Why transition metals are hard, why they show paramagnetism, why do they have high melting point and boiling point, so on and so forth. So we will talk about these properties. Sometimes these properties can be asked by the way of graphs. Okay, graphs will be shown. You'll have to see and observe the graph. You'll have to deduce the information, and then you'll have to answer the questions, which would basically be the same questions. Now, let's talk about the properties. Transition elements are hard. They have low volatility. They show paramagnetism. They have high melting point and boiling point, and they have high enthalpy of atomization. These all basically have the same reason, that transition elements have unpaired electrons. Why unpaired electrons? Because the definition of transition elements itself says that it has to have incompletely filled d subshell. Incomplete d subshell means that all of them are not paired. If all of them are not paired, that means there are unpaired electrons. If there are unpaired electrons, that means those unpaired electrons take part in bonding, metallic bonding. And when they bond, they increase the melting point and boiling point. How? The type of bonding that is there in transition elements is metallic bonding. Metallic bonding depends upon how many electrons take part in the bonding. Higher the number of electrons, stronger is the metallic bonding. So, they have unpaired electron, which leads to stronger metallic bonding. Stronger bond between atoms means you will have to give energy to separate those atoms. That means high melting point and high boiling point. Okay? Paramagnetism simply means unpaired electron. It's the direct consequence of unpaired electrons. Magnetic moment can be calculated using this formula, n plus 2 under root. Now, n means number of unpaired electrons. The unit is Bohr magneton. Now, another special thing about paramagnetism is you can be directly asked what is the magnetic moment of this ion. So you'll just have to write the electronic configuration of that ion, find out the number of unpaired electrons, plug those values in this formula, get the answer. But if the question is asked in form of MCQs, for example, cobalt 2 plus has the magnetic moment off, and then 4 values are given to you. Now, how would you find out which option is correct without having to calculate? Now, there's a relationship between magnetic moment and number of unpaired electron, that the magnetic moment almost always is around 0.75 to 0.9 more higher than the number of unpaired electron. What does that mean? That means if the number of unpaired electron is 3, the value should be somewhere around 3.75 to 3.9. Okay, so if the 4 options, if let's say cobalt 2 plus, cobalt is 3d7 4s2, 3 plus means 3d6. If it's 3d6, that means 1 2 3 4 5 1 2 3 4 5 6. Sorry, cobalt 2 plus I said. Cobalt 2 plus, that would mean 3d7. So this is 3d5, 3d6, 7. Okay, so it has 3 unpaired electrons. If it has 3 unpaired electrons, that means the value should be close to 3.75 to 3.9. So if your options have values like 3.75 and 4.5, 5.2 or 6.3. So obviously whatever value is like 4 point something and 5 point something and 6 point something, they are not possible. The very easy answer is the magnetic moment is around 0.75 to 0.9 higher than the number of unpaired electrons, right? I hope this helps. Then talking about enthalpy of atomization. Enthalpy of atomization, very simply put, is the enthalpy required to separate a matter into individual atoms. Now, if it has to be separated into individual atoms, obviously energy needs to be given. And if the interaction between those atoms, if the bonding between those atoms is very strong, you will have to give in more energy to separate those atoms. So obviously, stronger the metallic bonding, means higher enthalpy of atomization. Stronger metallic bonding would be a direct result of number of unpaired electron. More the number of unpaired electron, stronger would be the metallic bonding, and therefore higher would be the enthalpy of atomization. Now here are the two graphs which would show what I've been talking about. Now this one is melting point and atomic number. So we can see that as the number of unpaired electron increases, the metallic bonding would increase and therefore the melting point would increase. There's a dip around the center in the manganese. That is because manganese has half the filled electrons. Its d subshell is half filled. If its d subshell is half filled, it's sort of happy on its own. It doesn't want to bond with other atoms. So its metallic bonding would not be as strong. So that is why its melting point is lower than expected. And then as the number of unpaired electron decreases, the metallic bonding, the strength of metallic bonding also decrease. If the strength of metallic bond decreases, melting point also takes a dip. Same would be the scenario with enthalpy of atomization. Here also, as the number of unpaired electron would increase, the metallic bond would strengthen. If that happens, the enthalpy of atomization would increase. But then in the middle, when the d subshell is half filled, the enthalpy of atomization would take a dip because the metal would have no reason to bond with other atoms. So the bonding would not be as strong, and therefore the enthalpy of atomization would not be as much. Then again, as the number of unpaired electron decreases, there is a dip in enthalpy of atomization. Okay. Now, coming back to the properties, there's one very important property. Why do transition elements show variable oxidation state? When they show variable oxidation state means they show many oxidation states. Now, they have configuration, general configuration n-1 d1 to ns2. This is their general configuration. Now, the energy difference between the d subshell and s subshell is very low. Because of the low energy gap between the two subshells, the electrons present in them, they all take part in bonding. That is why it shows many oxidation state. These two electrons would take part in bonding, then one electron from D would take part in bonding, then the next electron would also take part in bonding, and the next would also take part in bonding. So you would see many oxidation states in case of transition elements because the energy gap between the two subshells is very, very low. Now, talking about the catalytic activity, many catalysts are transition elements. You have vanadium, you have nickel, you have platinum. They all show catalytic activities. Why do they show catalytic activities? Now, what is catalyst? Catalyst can catalyze or speed up a reaction in many ways. One of the ways is providing a large surface area for the reactants to come and bond with each other. Okay, so they they allow the reactant molecules to get adsorbed, and therefore react. Or in other words, they provide a high surface area, okay, for many reactant molecules to come and get adsorbed and therefore react. Second thing is they show variable oxidation state. Now, why is that important? Catalysts at times, they form temporary bonds with reactant molecules. When they form temporary bonds, that means their oxidation state is going to change. So if the compound or metal itself shows variable oxidation state, it's going to help, right? So since they show variable oxidation state, that definitely helps its catalytic property. Okay, so that's about it. Why do they show catalytic activity? Next is, okay, so the next property is that they are able to form colored compounds. Now, what is the color due to? Now, d orbitals are hardly ever degenerate. They break up into two levels, T2G and EG. Now, when biggest transition elements have unpaired electron, there is a possibility that electron jump will take place. See, if it's D1 is going to have one electron here, 2 here, 3 here, 4, either the electron would go up or down. Let's say it's going down. Then let's say this. So even if the configuration is 3D9, there's still a possibility that electron from here would jump from here because there's a space here. Okay, so what happens is when visible light falls on a transition metal compound, the electron will absorb some energy from the visible light, and the electron would jump to the higher energy level. Now, the energy that it needs to make the jump has an equivalent frequency. The light of this frequency gets absorbed to make the jump. Okay, now we have a color wheel, WebGear. So let's say to make the jump, the electron absorbed energy in the violet region of the visible light. In that case, the color that the compound would reflect would be yellow. If it absorbed the energy in the blue range, the color that would be shown would be orange. Okay, so the compound reflects the complementary color of the light which it absorbed to make the transition from the lower d orbital to the higher d orbital. The easier name for this whole process is DD transition. This DD transition is only possible if there is space for the jump. That means if the d orbital is incomplete. Okay, if the d orbital is completely empty, then obviously there is no electron for jumping, so that would not show color. And if it's completely filled, then obviously there would be no transition. If there would be no transition, there would be no color. But as long as there is even little bit of space, that means as long as the d subshell is incomplete, there is a chance for DD transition. Okay, so there's an opportunity for DD transition, which happens, and therefore the transition metal compounds show color. Now, transition element compounds also form complex compounds. They form complex because for complex to be formed, the metal ion has to accept electron, okay, from the ligands. Ligands are the one which donate electrons, and the metal ion has to accept it. And it would be able to accept if it would have empty d orbital, okay, which it has. So transition element, they have empty d orbitals, and because of which it can accept electrons from the ligands, and therefore it forms complexes. And actually that is another reason why they show catalytic activity. In catalytic activity, there's one more reason. They can form complexes. Complexes with reactant molecules. If they will form complexes with them, they are basically allowing them to react. Those are obviously temporary bonds, temporary reactions, okay? But definitely it helps. Next up is formation of alloys. Now, alloys are formed when they have similar atomic sizes. So like I said, when we go from left to right along the period, the atomic size decreases. But if you see, there is not much difference in the atomic sizes. See, it decreases, but from 1 to 2, it doesn't have, the atomic size of an atom, it's very close to its neighbors, right? So they have atomic size which are very similar to their neighbors. So if they have similar atomic sizes, they can easily form alloys, they can easily mix. Now here, the questions that can be asked is why they form alloys, and then sometimes the questions are asked as in which of the following is an alloy. So nichrome is an alloy of nickel and chromium, as the name suggests. Then you have steel, stainless steels. They are alloys of iron. And then there is bronze and brass. They are also alloys. Now, students often forget which one is bronze and which one is brass. So I have this trick which has helped me to remember which one is brass, which one is bronze. It's very silly, but I hope it helps you too. Now, see, brass has copper and zinc. Bronze has copper and tin. Now, they both have copper, which is obvious. The only confusion is between zinc and tin. Now, if you remember the symbol of tin, it's easy. The name of the alloy which has S has zinc, and the name of the alloy which has Z has tin. So it's the opposite. Okay, brass which has S does not have tin, it has zinc. Bronze which has Z does not have zinc, it has tin. It's very silly, but trust me, it helps. Now, next up, we would be doing questions based on them. All right. Now, when we talk about colored compounds, many times these questions come. Like, for example, why this is colored and the other thing is not colored. To answer them, you simply have to see whether there's a possibility of DD transition. That means whether there is incomplete D subshell. If the D subshell is empty or completely filled, the color won't be there because there won't be any DD transition. Now, copper 1 compounds are colorless, whereas copper 2 compounds are colored. Okay, so copper is 3D10 4S1. Copper 1 would be 3D10. Copper 2 would be 3D9. Now, obviously, since copper 1 is 3D10, the D subshell is completely filled. There is no possibility of DD transition. No DD transition. No DD transition means no color. Copper 2 plus, there is a possibility of DD transition because it's incomplete. The D subshell is incomplete. As simple as that. Oh, I think I did not talk about interstitial compounds. Never mind, we'll talk about that here. So, mention the type of compounds formed when small atoms like hydrogen, carbon and nitrogen get trapped inside the crystal lattice of the transition elements, and also give physical and chemical characteristics of these compounds. Now, the compounds, the name of the type of compound is interstitial compounds. Basically, when we talk about the crystal lattices of the transition metals, there are some voids, and these voids can be filled with smaller atoms. Smaller atoms like hydrogen atom, like carbon atom, like nitrogen atom. And when these atoms take places between the atoms of the crystal lattice, that means when they basically fill the voids, these type of compounds are called as interstitial compounds. Now, physical properties, they are hard. Obviously, when there is no space left, it's going to be very hard. It's hard. It has high melting point and boiling point, higher than that of the pure metal. When we talk about chemical, it's basically inert. Another physical property is it would have more or less the same conductivity, same conductance. Why? Because conductance depend upon the atom's ability to, like atoms' electrons, they move. When they move, they conduct electricity. So obviously these atoms are not going to disturb that. So the conductance doesn't change. Okay, they have the same conductance. They are harder. They have high melting point and boiling point because they are harder. So these are the physical properties. These atoms, when they take up space between the voids, they sort of make them unlikely to react. So they make them inert. Now, next question. Copper 2 is colored, zinc is colorless, scandium 3 plus is colorless, titanium 3 is colored. Again, this can be very easily solved with just writing the configuration and seeing whether the d orbital is incomplete. If it's incomplete, there's a possibility of d2 transition and therefore compound would be colored. If not, it would be colorless. So I guess this is something that you can try on your own. I am now moving on to next topic. Now we will be talking about oxidation states. The transition elements show variable oxidation states. And because of variable oxidation states, they have some oxidation states which are more stable than others. And that can give rise to a lot of board questions, right? So let's see some of them. Why do transition elements show variable oxidation state? We have done that before. It's because the N-1 d subshell and NS subshell, they have very similar energy, or they have very low energy gap between them. And because of that, all these electrons take part in bonding. So N-d and NS electrons, they take part in bonding. So since there are more electrons taking part in bonding, there is more variation in oxidation states. Now, these are one-word questions, one-word answer type questions. Elements which show maximum number of oxidation state. Now, obviously, the element, the transition element, which would have highest number of unpaired electron is the one which is going to show maximum number of oxidation state. So when we talk about the first series, it's going to be manganese. Okay. So even when we talk about oxidation state graph, it increases and then takes a dip as the number of unpaired electron decreases. The transition element which shows only +3 oxidation state. There's just one, scandium. Its configuration, scandium configuration is 3d1, 4s2. After losing these two electrons, it loses one more to attain stability, to attain the noble gas configuration. So it loses all three electrons all at once, so as to show +3 oxidation state only. Because after losing these two electrons with very slight extra energy, it would want to get rid of only one electron which is in the way of it getting noble gas configuration. So that is why scandium would lose all 3 electrons to attain noble gas configuration. The transition element which does not show variable oxidation state. So there is one scandium which we did. And then there is zinc also. Zinc also shows only +2 oxidation state, nothing more. But then zinc is not a transition element. It's a D block element. So if the question is the D block elements which show only one oxidation state, so you can say scandium and zinc both. But if it says transition element, you cannot say zinc. It would be scandium. Okay. Now, transition element first series which has the highest IE2, that means highest second ionization energy. Now, second ionization energy, highest second ionization energy means that after losing one electron, it has attained a stable configuration. That is why it's very, very reluctant to lose one more electron. That is why the second ionization energy is very high. So what are the possibilities? We have 3d5 4s1 configuration, which after losing one electron would attain stable configuration. We also have 3d10 4s1 configuration. So these two are the possibilities, but this would be chromium, this would be copper, but the answer would be this, copper. Why not chromium? Because as we go along the period, the ionization energy increases. So even between the two, they both will have comparatively high second ionization energy, but copper's second ionization energy would be higher than chromium's because along the period, ionization energy increases. So this is your answer. Similarly, transition element, the first series, which has highest third ionization energy. Same concept, 3d5 4s2 and then 3d10 4s2. But then it says transition element, so zinc is not a possibility. 3d5 4s2, that means manganese. Manganese, after losing 2 electrons, would attain half-filled configuration. That means now it would be very, very reluctant to lose one more electron. Okay, so that means its third ionization energy is going to be incredibly high. Okay, next up, the difference between the oxidation state exhibited by p-block elements and transition elements. Sometimes the question is between transition elements and non-transition elements. Now, when we talk about p-block, what comes to mind? Phosphorus, sulfur, tin, right? The oxidation states exhibited by phosphorus, +3, +5, 3 or 5. Sulfur, -2, +2, +4, +6. Tin, +2, +4. Now these oxidation state, if you can see the trend, they differ from each other by 2 units. Whereas in case of transition elements, as we have seen, they show many oxidation state all differing from each other by unity or by single unit. Okay, so if an element shows +2 oxidation state, it will also show +3, +4, +5, +6, +7. Example, manganese, right? So they differ from each other by unity, whereas in p block, the difference between the two oxidation state is 2. Okay, so that is the difference between oxidation state exhibited by p block elements and transition elements. Next, following ions are given. So you have chromium 2+, copper 2+, copper plus, iron 2+, iron 3+, and manganese 3+. Which one is a strong reducing agent? In these kind of questions, at times, E0 values may also be given to you. Okay, so strong reducing agent means something that is likely to get oxidized. Reducing agents get oxidized themselves. So a strong reducing agent would be very much eager to get oxidized. So which of the following ions would want to get oxidized? This is a possibility, and then this is also a possibility. How? Chromium 2+. Chromium was 3d5 4s1. 2+ means 3d4. If it loses one more electron, that means if it gets oxidized itself, it gets 3d3. Now this 3d3 is no ordinary 3d3. This is basically T2G3. That means the degenerate d orbital, which has broken into 2 sets, T2G and EG, this is filled, completely filled. And this is lower in energy than normal d orbital. Then obviously, this is more stable situation. Iron 2+, Iron normally is 3d6 4s2. So 2 plus would be 3d6. 3 plus would be 3d5. This is also stable situation, but no more stable than this. This is more stable situation. Okay, so strong reducing agent, which is very eager to get oxidized itself, is chromium 2 plus. Unstable in aqueous medium. Now, this you must remember, it's very commonly asked question in boards. Copper plus is highly unstable in aqueous medium. In aqueous medium, it undergoes disproportionation reaction and forms copper metal and copper 2 plus. So it gets reduced and oxidized. Now, why does it form copper 2 plus? Copper 2 plus, obviously, as we can see, it's the same metal, higher charge. Higher charge means higher charge density. If it has higher charge density in aqueous medium, it's going to be surrounded by this thing. This V basically denotes water molecules which have shape like this. Okay, so it would be heavily hydrated. It would be very heavily hydrated because it has much higher charge density. This hydration energy basically is released. So if it's released, that means it's stabilizing the whole situation. Okay, so copper 2 plus is stabilized by large release of hydration energy. Why copper 2 plus is heavily hydrated? Because it has high charge density, much higher than copper plus. Okay, that is why in aqueous medium, copper plus readily changes into copper 2 plus. Next, strong oxidizing agent. Strong oxidizing would be the one which would get reduced itself. It's something that is very eager to get reduced. Now, which one is very eager to get reduced? Mn3 plus. Mn3 plus. Manganese has the configuration 3d5 4s2. So Mn3 plus would be 3d4, right? If it's 3d4, it would rather get reduced, that means accept an electron and form Mn2 plus, therefore gives 3d5 configuration, which is half filled, therefore extremely stable. So manganese 3 plus is likely to get reduced itself, therefore it would oxidize others. Okay, now next question is, ionization energy of chromium is lower than that of zinc. Again, the answer lies in configuration. Chromium normally is 3d5 4s1. After losing one electron, i.e. 1, because the question is about i.e. 1, after losing one electron, it becomes 3d5. Zinc is 3d10 4s2. After losing one electron, nothing changes. Okay. Therefore, chromium plus is half filled, therefore very, very stable. This is still not completely filled. I mean, it is filled, but there is one more electron it would want to get rid of to attain a stable configuration. All right. The next question is, manganese show highest oxidation state of +7 with oxygen, but with fluorine, it shows highest oxidation state of +4. Explain. This question can be asked in a variety of ways. One of the ways that it can be asked is, why MnF7 does not exist, whereas Mn2O7 does exist. Okay, it can also be asked in the way that oxygen and fluorine both are able to attain high oxidation state out of manganese, but oxygen is more capable than fluorine. Why? Now, let's see. If fluorine is to attain the highest oxidation state, that is +7 with manganese, it has to form single bonds, because it forms single bonds only, 3, 4, 5, 6, 7. Okay. because fluorine, the configuration is 1s2, 2s2, 2p5, because it can form only one bond. Therefore, the bond has to be sigma bond. That means only single bond. So that means to attain the highest oxidation state, it would have to form MnF7, which is not stable, because obviously if these many fluorines would surround the manganese, obviously there's going to be electron-electron repulsion. There would be steric hindrance. Okay, so this compound is not going to be very stable one. But in case of oxygen, the good thing is that oxygen is able to form double bonds. Oxygen is able to form d pi p pi bond with manganese. Basically, it's the fancy way of saying that oxygen forms double bond. Double bond means one single bond, one pi bond. Now, pi bond would be formed between p orbital of oxygen and d orbital of manganese. Therefore, d pi p pi. Right? Now, since it's able to form a pi bond, a double bond, there's not as much crowding around manganese. So, if Mn2O7 structure is to be written, since it's odd number of oxygen, so I would guess that one oxygen is between two manganese, and then each manganese would get three oxygens. Now see, the situation here is not as crowded as the situation here. Manganese can accommodate 4 coordination number. So MnF4 is possible, but not beyond that. Okay, Mn2O7 is possible because even when it has oxidation state +7, it has only 4 atoms around it. Okay, which means that there's not as much crowding, which means this can be formed. This is stable, right? I hope this is not too messy or confusing. The only thing that you have to write is that since oxygen is able to form d pi p pi bond with manganese, Mn2O7 is not as crowded. The central metal ion is not as crowded as it would have been if MnF7 was to be formed. Okay. Now, next question is Mn2O3 is basic, whereas Mn2O7 is acidic. Now, this is a universal truth that lower oxidation state, lower oxides are basic for any compound, for any ion, any element. Lower oxides are basic and higher oxides are acidic. Now, why is that? Now, see, here Mn is +3 oxidation state in Mn2O3. In case of Mn2O7, the oxidation state is +7. Now, since this is lower oxidation state, that means it has electrons. It has more electrons than Mn+7, obviously. Now, since it has electrons, it can donate those electrons. If it can donate those electrons, that means it's going to act as Lewis base, right? Because Lewis base means it can donate electrons. Lewis acid would mean something that accepts electrons. And that is true for Mn+7. Mn+7 is highly positive, so it's more likely to accept electrons. If it's going to accept electrons, it's going to act as Lewis acid. That means it is going to be acidic. Okay? So therefore, Mn2O7 is acidic and Mn2O3 is basic. All right, let's move on to the next question. Here. All right, so we have some E reduction values. And based on those, we have to answer the 2 questions. But before I get to that, I need you to remember one thing. Very simple. Because what happens is students get confused with the meaning of reduction potential. So, if reduction potential, if E Mn M. If this is reduction potential, obviously, because going from a positive oxidation state to neutral, it's going to get reduced. So this is reduction potential. Or if going from a higher oxidation state to lower oxidation state, that is also reduction, like here. Okay, so reduction potential, if the reduction potential is positive, that means it's going to feel, that metal is feeling positive about reduction. That means it's likely to get reduced. If it's negative, that means it feels negative about the reduction. That means it's not likely to get reduced. But that's not like absolute truth. Basically, it's relative. You have to compare the value. The element with more positive E reduction value is going to get reduced, even if the other value is positive, but not as much. The metal that has higher positive reduction value feels more positive about reduction. So it gets reduced. The value, if let's say you have to compare two negative values, then also the one which is more negative reduction value, E reduction value, that means it feels more negative towards reduction. That means the less negative value, that one is going to get reduced. Okay, so you have to compare. And when you compare, say this. When you say this, things would become easy. Now, that is why basically standard hydrogen electrode, she has the E reduction value 0. So basically that is sort of neutral. If you pair up with the half cell which has E reduction value positive, so that half cell is going to get reduced and hydrogen electrode, hydrogen half cell is going to get oxidized. And if you pair it up with a reduction, if a half cell which has negative reduction value, negative E naught reduction value, then that means that it's going to get, hydrogen one is going to get reduced, the other one would get oxidized. Okay, so compare the values like that. Now, which one is a stronger reducing agent in aqueous medium, chromium 2+ or Fe2+? Now, reducing agent, that means it has to get oxidized itself. Okay, so let's compare these values. These are reduction potentials. Okay, these are reduction potentials. We want to see how oxidized, how likely they are to get oxidized. So if I just flip the values, if I write the value for M2+ to M3+, if I make it oxidation potential, the sign of this value would get reversed. So this oxidation potential for chromium would be now positive 0.41, and for iron it would be negative 0.77. So for oxidation, chromium is feeling more positive about oxidation. If this is feeling more positive about oxidation, it's going to get oxidized and therefore it's going to reduce the other one. Okay, so the answer would be chromium 2+. Okay. Now let's talk about the second question. Which is the most stable ion in +2 oxidation state and why? Now here again, you can compare the last thing. Most stable ion in +2 oxidation state, that means the one which is more likely to get reduced to +2. Which one is more likely to get reduced to +2? Cobalt. So obviously your answer is cobalt. Okay. Moving on to the next question. Draw the structures of chromate and dichromate ion and explain why dichromate is a better oxidizing agent. Now chromate ion, Cr(O4) 2 negative, dichromate ion, Cr2O7 2 negative. Now it's very easy to form structure of oxygen ions. What you have to do is draw the center metal ion in the center, then look at the charge. 2 negative charge, that means 2 oxygens are carrying negative charge, 1 negative charge each, and they would be singly bonded to the central metal ion. How many oxygens remaining? 2 more. Then they would be forming double bond with chromium. Okay, this is how we make the structure. Dichromate ion, now see, it has odd number of oxygens and 2 metal ion. 2 metal ions are hardly ever bonded to each other. They always have an oxygen between. Okay, so 2 chromiums, 1 oxygen in between them. This oxygen has made 2 bonds. We have now 6 oxygen atoms. Out of those 6, 2 would carry the negative charge, 1 here and 1 here. Then 4 are still there, so they will form double bond like this. So this is your dichromate ion, this is your chromate ion. Now, very interesting question that is asked is how many equivalent chromium oxygen bonds are there? If you look at chromate, it has, you would say, like students tend to say, that there are 2 equivalent chromium oxygen bonds. These are 2 equivalents and these 2 are equivalent. But no, this is actually a resonance situation. This electron would come here and this electron would go here. Similarly, this would come here and this would go here. So it's not fixed which oxygen carries the negative charge. It sort of goes around on all oxygens. So if I have to make a more apt structure of this, it would be something like this. They all have a rather double bond character than a proper double bond or a proper single bond. So all 4 CR bonds, CRO bonds are equivalent. 4 equivalent CRO bonds in chromate. Talking about dichromate, with the same logic, these 3 CR bonds and these 3 CR bonds are equivalent. So it has 6 CRO bonds which are equivalent. But this CRO bond is not equivalent. This bond is actually a little longer. Since this is a little longer, it's a little weaker. If it's a little weaker, it tends to break easily. And when it breaks, it releases oxygen, which oxidizes the other substance. Now, that is precisely why this dichromate is a better oxidizing agent. Because if you look otherwise, the oxidation state of chromium here is +6. Here also it's +6. So that means both are likely to get reduced to +3, which is a stable oxidation state for chromium. And in doing so, they would oxidize others. So if you look at oxidation state, they're both equally likely to be a good oxidizing agent. But because of this CRO bond being much longer and therefore weaker, this is a dichromate is a better oxidizing agent because it releases this oxygen quite easily. Okay. Now, write the formula of an oxoanion of chromium in which it shows oxidation state equivalent to its group number. Easy. First, we have to find out the group number. When we find out the group number, write the first series: scandium, titanium, vanadium, chromium, manganese, icon, copper, zinc. Now, the group number here would start from 3. Why? Because before this, we have alkali metals and alkaline earth metals. They are group 1 and 2 respectively. So from here onwards, group 3 is scandium group, and then group 4, 5, 6, 7, 8, 9, 10, 11, 12. Now when we talk about chromium, the group number is 6. So we have to write the formula of an oxoanion which shows +6 oxidation number. You can write any one of them. Chromium dichromate also shows +6. Chromate ion also shows +6. But you cannot write CrO3. CrO3 would also shows +6 oxidation state, but it's not an oxoanion. We have to talk about oxoanion. Okay. All right. Same question for manganese. Manganese group number 7. So we have 2 ions: permanganate ion, MnO4 negative, and then manganate ion, MnO4 2 minus. Okay. This one will have +7 oxidation state. If you find out the oxidation state of this, it would be +6. So this can't be the anion. This one has to be the anion, which has oxidation state equal to the group number. Okay. All right. I hope this has helped. I'll see you in now part 2.